Okay, guys, I think we've got this figured out. So let me just get you on here and share screen and this one and this one and this one and here. Does this look good? Give me a thumbs up, people. Does this look good? Yay! Hi there, Janowski. Hello, Ponder. Manter, hello. Okay. Yay, it's working. Good. Thank you for sticking with me here. So, the last puzzle that we dealt with, this day is going to be a recap of some of the puzzles that we did because I've had feedback from some people about them and some extensions. And then I have one new puzzle to introduce. The one puzzle I didn't get feedback on was this one, the spaghetti one. So I'm not going to talk about it. Instead, I'm going to jump to one that I did get feedback on, and it was this one here. This is a beautiful image. No, let's not do that. Okay. So this is an image by Carol Highsmith, and you can see the swamp, and 3 people independently came up with a way, basically the same solution, to show that this problem can be solved even for a very large number of frogs. So we're going to go through that proof that they did, essentially. It's really a proof, but it's really cute. So here it goes. So they didn't start off big. Instead, like many great problem solvers, they started out really small. They started out, can we solve this problem with 2 frogs? Remember that 1 frog jumps 1 lily pad. So here we have this, and we have a party of 2 people of 2 of these frogs on the same lily pad. So they're happy. Okay, that was pretty trivial, right? But then these 3 people went on to explore, well, what happens with 4 frogs? Well, we can really do the same thing. We can do frog number 1 jumping, and then we can do frog number 3 jumping. I'm going to jump them at the same time, but you could jump them one after another. Boom, boom. They go like this. But this kind of looks like the simple problem we just solved, right? These are 2 stacks of frogs separated by 2. Remember, 2 frogs jump 2. So now I'm going to take those 2 and I'm going to jump 2. 1, 2. We've solved it. Then they said we should go on to 8. And we should take all of the frogs on the odd number lily pads, and we should jump them. Now you can jump them any order you want. We're going to jump them all together here. But this is kind of like the 4 frog problem, and we've already solved the 4 frog problem because these 2 jump 2, and these 2 jump 2. And this is kind of like the 2 frog problem. We're going to get these all here, jumping, and we've solved the 8 frogs. What number do you think they suggested trying next? Of course, they suggested trying, go ahead, tell me. So Hardy, this is not supposed to be hard. What is supposed to be hard is that you guys have to come up with the pattern. And these 3 people did come up with a pattern. So here we go. This pattern here, and they jumped like this. So this was a very easy way to show. Here we're going to go like this, and we're going to go like this, we're going to go like this, we're going to go like this, and then we jump like this. And then this looks like the 4 frog puzzle. We take these ones and these ones, and they all jump. And then this all looks like the, oh, I forgot a frog. Come here, frog. Okay, And this looks like the two frog problem. So we can jump this one over here. So I just thought that was a very, very nice solution. And that was, so what's the next one? Well, you just multiply by 2 again. So we can solve for 2, then 4, then 8, 16, 32, 64, 128, 256, 512, 1024. Keep on going forever and ever. Okay. Now, Trevelyan created this photograph, and one of the people actually suggested to do this for 3 frogs, and their solution, you can imagine that their solution was to solve it for 3. And if we solve this for 3, then we can also solve it for 3 times 3. Okay, here we go. Let's do it for 3 times 3. So we're going to treat each one of these groups of 3 frogs the same. So no, we're not going to do that. Yeah, so we can solve it like this. And then this group of frogs goes like this, and this goes like this. Okay, so now I want you guys to tell me, yes, Hardy, I want you to try 18 frogs. So can we do it for 18 using the techniques of these 2 different types? We can also do it so this looks very much like the 3 frog problems. We can go like this, and we can go like this. Okay, and then of course we could do 27, 3 times 3 times 3. Okay, but your question of can we do this for 18 frogs, we're going to try it simpler. I want you guys to use the same technique that we've done here. By blending the 2 and the 3 solution, can you solve it for 6? Okay, so think about that. And think about it for 15 seconds, and then tell me how I should proceed. Okay, so any idea how to begin? Well, if you remember with the yeah, so the first way that we can try it is we can do it like this. Remember, with choosing all of the odd ones, and we just jump on top there. So we can do that, and then we can treat this as a 3 frog solution. So 2 frogs jump 2, 2 frogs jump 2. Right. Is there another way to do this? Okay, so that's from Ashukli. Okay, so is there another way to do this? Sure, we can, instead of doing that, we could do we can group frogs in groups of 3 first. So we could go like this, and like this, and like this, and like this. And now we do the 2. Now this is kind of like the 2 frog solution. There we go. So 2 very different ways to solve the same puzzle. This is kind of like non-commutative multiplication. So 2 times 3 does not look exactly the same as 3 times 2. Now, the frogs all get to end up partying in the same place, but how we got there was a little bit different. Okay. Bret Hart created this beautiful image of a swamp. And you can imagine that in order, I'm not going to keep on going with this, but you can see that if you solve for 5, then you can solve for 2 times 5, and you can solve for 3 times 5 just by grouping them differently. Okay, we're not going to do that now. Okay, we're going to keep on going. This puzzle here, this puzzle here, this is our new puzzle for today. Are you guys ready for the new one? thumbs up if you're ready for the new puzzle. This is called Cardboard Mountain. Okay. In this cardboard mountain, you're going to be climbing from the base. And each time you choose a circle above you, it must be right in the middle of the two circles underneath. Okay? So if this is a 6, what could I put here? Which number could I put here? Well, you can choose any number. I will tell you that you cannot go negative. Okay, so this is 0, 1, 2, 3. These are the numbers you can put inside. Okay, 5 and 7. Yeah, so thank you very much, Wu. We can put 5 and not 6, 5 and 7 there, because 6 is right in the middle. Okay, give me another 2 numbers that we could, oh no, give me 2 numbers that you can put under 5 now. Okay, 2 numbers under 5. So those have to, those 2 numbers have to, 5 has to be right in the middle. 4 and 6. Yeah, you can put 4 and 6 there. Unfortunately, you have messed up the mountain avalanches and you guys are in deep trouble because you have 2 6s on there. You're not allowed to have the same number in 2 places on your mountain. Okay, we're going to go back up to the top and go again. Yeah, you can't have the same number. You had a 6 at the top and you had a 6 in the middle. No, that's an avalanche situation and you do not want to do that. Yeah, so try again. 2 numbers that 6 is right in the middle. Okay, are you guys still with me? Okay, 4 and 8. Yeah, so 4 and 8. Okay. Okay. And now I need 2 numbers that average or that are above and below 4, so that 4 is right in the middle. 1 and 3, 2 and 6. Who said 2 and 6? Moore, we've already got a 6 at the top. So if you put a 6 there, you've messed us up. 3 and 5 are good. Yes, 3 and 5 work. Okay. So ponder. You can see that 3 is a distance 1 from 4, and 5 is a distance 1 from 4. You can see that 6 is a distance 2 from 4, and 8 is a distance 2 from 4. So 6 is right in the middle of 4 and 8. Get it? 4 is right in the middle between 3 and 5. Now, we've got 5 here. 5 is distance 3 from 8. What number do we need to have over here so that 8 is right in between 5 and that other number? What other number do we need over there? Okay. So we've got 9, we've got 11, we've got 10. So let's see if 9 would work. 9 is distance 1 from 8 here, but 5 is distance 3. So no, 9 does not work. Okay. 11, does that work? 11 is distance 3 from 8, and 5 is distance 3 from 8. Ah, we've got it. Good. So 11 works. Good. Good. Everyone is in agreement. We are cool. Okay, but it's going to get harder because what on earth are we going to put here? We can't duplicate anything. That's our problem here. So if we put a 2 here, as someone suggested, what would we have to put here? We'd need to put a 4 here because that would mean 3 would be right in the middle, but we've already got a 4. So we know that 2 can't work. Oh, it's going to be difficult. Maybe it's impossible. if we put a 1 here, then what are we going to have to put here? Stop spamming, Hardy. That's enough. I understood. You do not need to yell. Yeah. So if you put a 1 here, then 1 is distance 2 from 3. So 3 plus 2, that would be 5. But that's not good because we've got another 5 here. So we're totally messed up. If we put a 0 here, okay, then 0 is distance 3 from 3. 3 plus another 3, that would be 6. But we've got 2 6s now. So this is a failure, a total failure. So it is back to the drawing board. Now, I put the number 6 at the top. Perhaps you guys would like it. It'll be easier to climb this mountain, ironically, if you put a larger number at the top. Yeah, exactly. So Whitaker asks a great question. Why did we start with the 6? You started with the 6 because I told you can start with the 6. And I've tried this puzzle. So you want to start with a 10, Herndon? I'm happy with an 8 to 10. Yeah. What are we going to do? Next number that comes through, we'll go with that. 8 or 10. What do we want? 10. Okay, we're going to go with the 10 at the top. Okay, so I want two numbers here and here that are the 10 is right in the middle between those two numbers. So like 0 and 20 or 1 and 19, something like that. Okay, so go ahead, give me some numbers. So yeah, 9 and 8 isn't going to work because, so if we put 9 here and 8 here, well, 10 isn't in the middle of those. 10 is bigger than both of those, so that's a disaster. Okay, we're going to go 5 and 15. This was Janowski's idea. Okay, there we go, 5 and 15. I need two numbers to go on either side of the 5. So we have an example of, oops. So we're going to put a 4 here. And what are we going to put here? 6 there. Okay, and yeah, that would work because that's distance 1 from 5, and that's distance 1 from 5. Yeah, so we've nailed it. Okay, go ahead. What are we going to put? Oh, this one we should be able to calculate now. Okay, so we've got 15 has to be in between 4 and this other number. Okay, so what is the distance between 15 and 4? And then let's figure that out. So it certainly can't be 16 because 16 is only one distance from 15. 11 also doesn't work because that would be 11. 11 and 4 are both less than 15. 26, let's see if 26 works. So 26, what's the distance? What's 26 minus 15? That's 11. 15 minus 4, that's 11 too. That looks good. Okay, we are set. Where do we go from now? Where do we go? What? Let's put one right here, smack dab in the middle between 6 and 4. Oh, you want to go over here. Okay, so Ponder's saying 25 and 27. Okay, is that going to work? So is that going to work, guys? This is Ponder's idea. Has he taken us down a wild mountain path that is going to end in our destruction? Is this good? Well, the problem is, what do we put here? Right? We can't go negative. I mean, we're not going into a valley. We are climbing a mountain. So these all have to be 0 or greater. And the difference between 25 and 4 is 21. So how do you go 4 minus 21 and stay positive? So no, Ponder, you can't go 25 and 27. Too bad. Wrong. Okay. Yeah. Okay. Yeah. But it's fun to try, right? Like if you don't try to climb these mountains, you don't figure out that, yeah, some of those are nasty. 0 and 8. Okay, we're going to try 0 here, and we're going to try 8 here. So this is Wu's idea. And if this is an 8, and if this is a 0, okay, first of all, let's go this side. If this is a 0, then what has this got to be? Okay, for it. So the idea for it is that whenever you're going up this mountain, if a circle is above these two circles underneath, this circle must be right in between these two circles. So you can see that 5 is right in between 6 and 4, right? It's right in between. And 15 is right in between 4 and 26. Okay, it's right in the middle. So 15 minus 4 is the same as 26 minus 15. That's another way to think about it if you want to do subtraction. Okay. Yeah, you can also say that it's an average. For those of you who know the word average, the circle at the top is the average of the two circles underneath. That's right. Okay, so is this a fail or is this good? Yeah, so Whitaker's suggesting that this might be a fail. Heatley is suggesting 7. So does this work? Is 7 and 0? What's right in between 7 and 0? Well, it's certainly not 6. 6 is much, much closer to 7 than it is to 0, right? So 7 certainly is not going to work. Okay, what could work in there? 12? Yeah, 12 would work because, yeah, 6 is right in the middle between 0 and 12. That's exactly right. Yeah, good. Okay, and over here, the last one. Janowski says, Moore says 44. Let's try 44. Does that work? So that would be, yeah, I think that's right. Yeah, that works. 26 is right in the middle of 44 and 8. Okay, so you guys managed to solve this with 10. But the question is, these mountains actually become harder and harder as that number at the top becomes smaller and smaller. So your challenge is to find the smallest number that you can put at the top. Now, I will tell you, for this mountain, the smallest number is 6. Okay, you can get down to 6. I don't think you can get smaller than 6. So that's a challenge for you guys. But that's not the mountain that you guys can get to work with. You get to work with this mountain. It is even bigger. It is extremely difficult to find the smallest number that can go at the top. And I'm not going to tell you what it is because I really am not sure that I know what it is. I think I know what it is. So next week, you guys can come to me and can suggest what you think the smallest number that you can get in that top part of the mountain is. Okay? And the answer, Herndon, is certainly not 0, because you remember there is a rule that you can't have duplicate numbers, and all the numbers have to be positive. So if you put 0, let's say even you put like 1, let's say 1 at the top, okay, well, then the only way that you can solve this is the next line is 0 and 2. Okay, that's fine. You're doing fine so far. But then what do you put here? Okay, let's say like you could put 0 and 0, but then you've got multiple zeros. So yeah, this is not simple. This is a tough problem. No doubt about it. This is a very difficult problem to find the lowest number that can go at the top here. So don't fool yourselves. You're not going to solve this one quickly. And I think it's also interesting to try to find for really large mountains, like this one you could say is still a small mountain. For really large ones, do you have any sense for how to figure out some kind of pretty good solution? It might not be the best, so that would be something else you could think about. But the most important one is finding out for this, what is the smallest number you can get at the top? Okay, Heatley suggests 7. Maybe. I think you're going to have a tough time with 7. Eventually, they do get impossible. If you drop it down too far, they become impossible. So I'm not telling you, but you will not figure this out quickly. I did not figure this out quickly. I think I designed this puzzle about 3 years ago, or maybe 5 years ago, and I still don't know that I have the right answer. So, okay, back to the frogs, because I wanted to show you that there is a way that you can solve any number, no matter if it's 1,000,000 frogs or 5,000,000, something that you're not going to do by hand. But there's a beautiful mathematical proof that you can see that this works for all frogs. And I will show you the mathematical proof without even talking. Are you ready? This is a no-talk mathematical solution for you guys. I start in the middle, right between 11 and 1. We've just climbed a mountain. We know what in the middle means. So we're starting in the middle. We jump either direction. And oh, I'm supposed to not talk. Okay. And I'm lying. I'm going to talk. Just for those people who haven't seen the problem before, you have to remember that 7 frogs now, they jump 7. So I'm going to jump over here. 8 frogs jumps 8. 9 frogs jumps 9. 10 frogs jumps 10. And you can see that this pattern can repeat no matter how many frogs you have. I know I can solve this problem for 1,000,000 frogs. It's easy. Okay, so that is a kind of mathematical insight that is at a higher level than just solving for a puzzle that is 7 or 8 or 9. Yeah, you can solve for those, but always look for that deeper mathematical insight that allows you to solve for an infinite number of puzzles like that. Okay, A. Kazemi suggested that this was a puzzle that could not be solved. So remember, one of the challenges, and the challenge that I was most interested in, was if you allowed your opponent, or if you're allowed the frogs to make 3 really bad moves, can it always still be solved? And so A. Kazemi thought that this was an example that it could not be solved with 11 frogs. And again, I'm interested in how many frogs you can have, because I think it does become solvable if you have a large number of frogs. So here the question is this solvable with 11 frogs and 3 moves? Okay, go ahead, try to solve this. Is Kazemi correct or wrong? So we're going to go 1 to 3. Nope. So Dubowski, I didn't tell you this time, but 1 frog moves 1 space, but frogs can never jump onto a lily pad without other frogs on them. Okay? You win whenever all your frogs get on the same lily pad. So Dubowski, you can't go from 1 to 3. Or maybe that was a question that you had for another one. Anyway, go ahead, guys. Make a suggestion. How am I going to solve this and show Kazemi is wrong, that this is solvable? Or is Kazemi correct? Have we found an example of something that is not solvable? 7 to 5. Okay, we're going to go 7 to 5. 11 to 10. 11 to 10. Thank you, Willis. Thank you, Heatley. Borowski, you're back. Okay, 10 to 8. Okay. 3 to 1. You can't go 3 to 1. Whoever suggested that. Steele, yeah, you can't go 3 to 1 because on 3 there are 3 frogs. They're going to jump 3 spaces. So 1, 2, 3, they actually fall off the lily pads. Yeah. So that's not going to work. 9 to 8. Okay, 9 goes to 8. Good. And now what are we going to do? Now we're in a little bit of a pickle, aren't we? Yeah, I think we're in a little bit of trouble here. 5 to 8. Yeah, we can go 5 to 8. That's correct. So now we have 7 on here. 1, 2, 3, 4, 5, 6, 7. We can move over here. 8 to 1. But that's as far as we're getting. So that was an example as a failure. So Kazemi might be correct that this is impossible to solve. Only 3 moves. Oh, and let me show you those 3 moves. You can see how I did it, how he did it. So, or she. I don't know if Kazemi's a woman or man, girl or boy. So 1, 2, 3. Okay. Yeah. So that's I can leave that with you. That is so that's a question. If Kazemi has come up with an example 11 frogs long, or if this is not impossible. So that's a question. Certainly, I think for 12 frogs and more, everything is solvable. With only 3 wrong moves, I think everything is solvable. But yeah. Okay, we have Steele suggesting 3 to 1 again, 1 to 5. So 3 cannot go to 1, guys, because there are 3 frogs here. Okay, 3 frogs jump 3. 1, 2. It's only 2 spaces to get to 1. So Steele, yeah, you cannot do it, Steele. 3 to 1, your very first move fails. Understand? 3 to 5 also doesn't work because that's also a 2-step jump light. 5 to 1, yeah. 3 to 5 does not work. That's a 3 distance 3, but yeah, you need to be the only place this one can move right now is to 6, and 6 is 6 doesn't have frogs on it, so it can't move there. So this one cannot move right now. 7 to 5. Yes, we can do 7 to 5. That's fine, light. Yep. So that's true. We can do that. Yeah, you don't feel like a dummy. Like one of the most important things whenever you're exploring with mathematics is to feel free to fail. Do you think that I don't fail all the time? I fail a lot, and it's just a time to drink a little tea and to say, okay, I can tackle that again. Because yeah, so failure is a part of being a mathematician. You're going to fail a lot if you become a mathematician. In fact, most things in life, if you really are at the cutting edge, if you're not repeating something that other people have done, you're going to be failing a lot. So don't worry about failing. That means that you're really trying. So yeah, do not feel badly at all. Okay, 5 to 8. Yeah, that's good. Light. Yeah. What are we going to do now? 8 to 3. Okay, 8 to 3. How do people like that? Okay, no, that was the wrong move. There's only 4 here. 1, 2, 3, 4. So that would only get us to 4. Get it? Yeah, so that doesn't work. You can't do that. Correct. Okay. 9 to 8. Someone suggested this. Oh, now we could do that. Shall we do that now? Okay, yeah, we can do that now. Now we can go to 8 to 3. Okay, there we go. So now we've got 1, 2, 3, 4, 5, 6, 7, 8. We've got 8 here. What do we do? 1, 2, 3, 4, 5, 6, 7, 8. Really? That's too bad. 1, 2, 3, 4, 5, 6, 7, 8. Yeah. Looks like we can go 3 to 11. Oh, this might actually work, because then we can go 10 to 11. So I am looking optimistically here, because this is now 10. There's 10 on here, 10 on here, and yeah, the difference between 11 and 1 is 10. We have managed to beat this. So Kazemi, I'm sorry, but you've made a mistake. This is solvable. It is not unsolvable. So but Kazemi, that was a beautiful. This was not an easy puzzle to solve. So hats off. I was not sure that this was solvable or not. So very, very good puzzle for us to be working on. Yeah. So I have not yet found a puzzle with 11 frogs with just 3 moves that is impossible. Now, I don't know that I'm still trying, but I haven't found one. I don't use computers. So if you're a computer scientist out there, you can probably code this and prove one way or other that you can find an example, or you can find a counterexample. You can find something that doesn't work. But I like to do it by hand. I don't know. I just enjoy puzzling with these things, and I have not found one yet. And I've worked quite hard, not really hard, like by quite hard, probably maybe an hour. Okay, so not super hard. But yeah, I'd be really interested if anyone finds a puzzle of 9, 10, or 11. And I don't think, like I said, I'm pretty sure that 12 and above, it will always work. And I'm pretty sure that 11 always works. But anyway, you can experiment here. Give us your puzzles. You can put them onto the social tab in Dexter. You can also just email me, gord@mathpickle.com. If you're looking at this on my website, you can just email me directly. Okay, so that is it for today, and I love getting your responses and looking at these. And on Monday we will do a new puzzle, and we'll be looking at some of your responses from the last puzzles that we've looked at, whether it's the uncut spaghetti or this new mountain cardboard mountain problem. So we'll look at some of your responses from the previous puzzles too. Take care, everyone. And yeah, I know it's a tough time if you're in quarantine, if you know people are sick. My heart is out for you. So you take care, and thinking of you. See you on Monday. Bye-bye.